Good morning, dear students. Today we are going to discuss about the second lesson, current electricity, in which specifically we are going to discuss about the microscopic model of current, which explains about Ohm's law. Already in the previous session, you people have discussed about the movement of electric charges through a conducting material when the ends of the conductor are applied with a certain potential difference V. Here, in this microscopic model of current, we are going to discuss about the movement of electric charges, or in other words, I can say the flow of current due to the application of electric field through a given metallic conductor or through a conducting material. So, microscopic model of electric current deals with the application of electric field across a metallic conductor, which makes current to flow through the conductor, or which creates a current to flow through the conductor. So the application of electric field makes the charges to move in a definite direction, which results in a flow of current that is going to be discussed under microscopic model of current, right? Here in this microscopic model of current, we are going to derive a relation between current and drift velocity, and then we are going to discuss about the current density, relation between current density and electric current, and then we are going to discuss about the relationship between current density and the applied electric field. So finally we are reaching the target that if an electric field is applied across the or applied through the metallic conductor with the application of potential difference, then how it results in the flow of electric current. This is what is going to be discussed. So in other words, I can say we are going to get into the conductor, into the metallic conductor, where the movement of charges takes place with the application of electric field. In macroscopic model of electric current, we are going to bring out a relationship between the application of external potential difference V and a current I flowing through the conductor through a metallic conductor of resistance R. So there is a marking difference between these two. In microscopic model of electric current, we are going to discuss about the flow of current or flow of charges inside the metallic conductor. And in macroscopic model of electric current, we are going to discuss about the relationship connecting voltage, current, and resistance of the metallic conductor. Right. In microscopic model of current, in order to bring out the relationship between current and drift velocity, what are the things we are going to do? What are the steps we are going to follow? First, we are going to calculate the drift velocity possessed by the electron. With the help of drift velocity, we are going to calculate the number of electrons present in a given volume of a conductor. And third one, we are going to calculate the total charge existing in the given volume of the conductor. And the fourth one is that we are going to substitute the total charge in the given volume of a conductor in the relation for electric current I equals dq by dt, from where we are going to bring out the relationship between current and drift velocity. So, to derive expression between current and drift velocity, we are going to follow 4 different steps. First one, we are going to write the expression for drift velocity. Second one, we are going to calculate the number of electrons in a given volume of a conductor. And third one, we are going to calculate the total charge of the electrons in a given volume of the conductor. And then with the help of charge and with the time, we are going to calculate the current. Automatically, it will give you the relationship between current and drift velocity. Let us consider a conductor, metallic conductor of length L, and it has an area of cross section, let us say A, area of cross section A. I am going to assume a small elemental length of conductor in this one. Let me say its length is taken dx. Dx is nothing but Vd into dt. drift velocity multiplied by time, Vd into dt, Vd into dt. And we can say here the electrons are drifting towards one particular direction. How these electrons are getting drifted? How these electrons are getting drifted? So we have taken a given conductor whose length is L, its area of cross section is A. Let me say a potential difference, external potential difference V is applied across the ends of the conductor so that it generates an electric field inside the conductor. So electric field will act from plus to minus. See, this is plus and this one is minus. So electric field will act in this direction, E vector. So electric field acts from right to left. So in this electric field, if negatively charged electrons are existing, they will be attracted towards the positive potential. So drift of electrons takes place from left to right. Electric field acts from right to left. Electrons are getting drifted from left to right. This is how the electrons are said to be moving. So electrons are said to be moving from left to right. Let us say small n be the number of free electrons per unit volume of the conductor. See, this small n here refers to the number of electrons per unit volume of the conductor. Number of electrons per unit volume. What does it indicate? So n refers to the number of electrons present in 1 meter cube volume of a conductor. 1 meter cube volume of the conductor. So number of electrons per unit volume of the conductor. Let us say n be the number of free electrons per unit volume of the conductor. And all the electrons inside the metallic conductor are getting drifted from left to right with the same drift velocity Vd. See this idea. They are moving with the same drift velocity Vd. They are moving with the same drift velocity Vd. So you have taken a metallic conductor and it has a length L, its area of cross section is A. The ends of the conductor are connected by a source of potential difference, let us say V, so that it produces an electric field across the ends of the conductor. Electric field acts from right end of the conductor to left end of the conductor. And we can say here there are small n number of free electrons per unit volume of the conductor. All these electrons, when subjected to this electric field, will get drifted towards the right, from left to right. So field will be acting from right to left. Electrons will be moving from left to right. See this diagram. Electrons are moving from left to right. Electric field is acting from right to left. What is the direction in which the force acts? As you know from electrostatics, I can write F vector is equal to minus of E into E vector, which indicates that the force and the electric field acts in the opposite direction because of the presence of negative sign. As electrons are negatively charged particles, we can say here the force and the electric field will be acting in the opposite direction. F vector equals E into E vector. So in this particular case, we have listed out what are the things associated with this diagram. So electric field acting from right to left, electrons are drifting from left to right. So they are moving with a constant drift velocity, or in other words, all the electrons are moving with the same drift velocity Vd. So the drift velocity with which the electrons are moving is said to be Vd. Now, we can write the expression for drift velocity. Drift velocity can be expressed as Vd can be expressed as dx divided by dt. Actually, you know very well, velocity is distance traveled by time taken. Here in this diagram, you can see dx is the distance between the two assumed, or the length of the assumed conductor. Length of the assumed conductor, dx is the length assumed. We can say here, the electron takes a time interval, let us say dt, or the electron covers this distance dx in a time interval dt with this drift velocity Vd. So I am giving out the expression Vd equals dx divided by dt. So idea is simple. Drift velocity Vd equals dx by dt is a very simple format. Velocity equals distance traveled by time taken. Dx is the distance that the electron has to cover in a time interval dt. So Vd equals dx divided by dt, from which we can write dx equals v dt. Dx equals vd into dt. Let me say this is equation number 1. Dx equals vd into dt. Distance traveled equals velocity multiplied by time. Now, we have to calculate the number of electrons in a given volume of the conductor, or number of charged particles in the given volume of the conductor. In order to calculate the volume of the conductor, we can say here, we have assumed a small length of this metallic conductor dx. A is the area of cross section of the conductor. A is the area of cross section of the conductor. When this area multiplied by length, this will give you the volume. Actually, we are going to calculate this volume. And we are going to find out the number of electrons existing in this given volume of the conductor. Number of electrons existing in the given volume of the conductor. Fine. So we can say here, we can show here, now to calculate the number of electrons in the given volume of conductor, I can write N, capital N is equal to the capital N can give you the total number of electrons in the given volume of the conductor, where N is equal to volume multiplied by the number of electrons per unit volume. Capital N is equal to, I can write the expression as volume multiplied by the number of free electrons per unit volume. So for unit volume, small n is the number of free electrons existing. So what is the number of electrons in a given volume? So multiply the given volume into number of free electrons per unit volume, so that you will be getting the total number of electrons in a given volume of the conductor. And the volume of the conductor, as I told you already, is the product of area multiplied by distance, length, area into length, A into dx, multiplied by number of free electrons per unit volume is small n. So volume multiplied by number of free electrons per unit volume will give you the total number of electrons in the given volume of the conductor. What is dx here? I can mark this as equation 2. What is dx here? From expression 1, we have vd into dt. So on substituting the value of dx in this expression, we will have a into vd into dt into n. So this expression will give you the total number of free electrons in a given volume of the conductor. Total number of free electrons in a given volume of the conductor. We got total number of electrons. Now, what is the total charge existing in the given volume of the conductor of length dx? What is the total number of charge or total amount of charge existing in the given volume of the conductor of length dx? So we can write here the total charge existing, total charge in the given volume dq can be calculated by multiplying charge with the total number of charges. If one single electron has a charge E, whose magnitude is E, if there are 100 electrons, what is the total charge? 100 into E. In the same way, dq is equal to n into E, because there are n number of electrons in the given volume of the conductor. Because there are n number of electrons in the given volume of the conductor. So I got total charge in the given volume, dq equals n into E. Substitute the value of n. Let me say this is equation number 4. Substitute 3 in 4. Substitute 3 in 4. What will you have? dq equals n is a vd dt. Vd is v suffix t. dt into small n into e. See, instead of n, I have substituted this one, and the charge has been taken as it is. So I can write dq equals n a e vd into dt. vd into dt. Now, what is the amount of current flowing through the given volume of the conductor? So we applied a potential difference because of which an electric field is existing throughout the metallic conductor from right to left, so that the electrons are experiencing an electrostatic force. They are getting drifted from left to right. They are drifted from left to right, which results in a flow of current, and that current has to be calculated now. I equals dq divided by dt. As you know, by definition, it is the rate of flow of electric charge through any given cross-sectional area of a conductor in unit time. So I equals dq divided by dt. dq is n a e vd into dt divided by dt. So this dt gets cancelled out. You will have n a e vd. So this is the relation connecting current and the drift velocity. I equals n a e vd. I equals n a e vd. Current is a scalar quantity. Current is a scalar quantity. Its unit is ampere. Current depends upon the number density of electrons. Current depends upon the area of cross section of the conductor. It depends upon the drift velocity of the electrons. It also depends upon the drift velocity of the electrons. So current I equals n a e v d, relation connecting current and drift velocity. So what all we did is that we first calculated the drift velocity of the electrons, which are moving from moving through a distance dx in a time interval dt. So we have taken it as vd equals dx divided by dt, from which dx has been calculated, and we are calculating the number of electrons in a given volume of a conductor. Already we saw small n be the number of electrons per unit volume of the conductor. So if you know the number of electrons per unit volume, we can calculate the number of electrons existing in a given volume of the conductor. So capital N is taken as the number of electrons in a given volume of the conductor. To calculate the number of electrons in a given volume of conductor, we are multiplying volume into number of electrons per unit volume. So n equals adx into n. Adx is the volume. Area into length gives you the volume. So adx into n. N equals avd into dt into n. So total number of electrons has been calculated. This many number of charges are there. If electron possesses charge E, then total charge in the given volume of length dx is dq equals n into E. dq equals n into E. N is substituted in this expression. We have calculated dq. So with the help of dq, we are determining the value of current. I equals dq divided by dt. So if I equals dq by dt, on substitution of dq, you are getting NaEVD. NaEVD. So the relation connecting current and the drift velocity is I equals NaEVD. I equals NaEVD. Right. Now we shall speak about the relation connecting current density and current. Current density and current. What is current density? What is current density? If you look at the definition for current, it is the rate of flow of charge through a given cross-sectional area of a conductor. Rate of flow of charge through a given cross-sectional area of a conductor. What is current density? What is current density? Current density is the rate of flow of charge through any given cross-sectional area of a conductor in unit time. J equals Q by T divided by A. Or otherwise, we can simply say current density is the amount of current flowing through a given cross-sectional area of a conductor A. J equals I divided by A. J equals I by A is defined as the current per unit area of cross section of a conductor. Current density is represented by the letter symbol J, and we can write the expression as J equals I divided by A. J equals I divided by A. Current density is defined as the flow of current through a given cross-sectional area of a conductor. Current density is defined as the current flow through given area of cross-section of a conductor. J equals I divided by A. It's a vector quantity actually. It's a vector quantity. Current density is a vector quantity. Current density is a vector quantity. Its unit is ampere meter per minus 2. Ampere meter per minus 2. Its unit is ampere meter per minus 2. So I can write it clearly. Ampere, its unit is ampere meter per minus 2. Dimensional formula is ampere L power minus 2. Ampere L power minus 2. This is the unit and this one is the dimension for current density. What is current density? Current density is defined as the current flowing through given cross-sectional area of a conductor. Current density is defined as the current flowing through given cross-sectional area of a conductor. J equals I divided by A. We saw the expression for current as J equals, or current as I equals NAEVD. You substitute this current in this expression. Let me say this is expression number, let us say some 5. Substitute the value of current in expression 5. You will have J equals NAEVD divided by A. This gets cancels out. We will get NEVD. Current density is given by the expression NEVD. Current density is given by the expression NEVD. Current is NAEVD. Current density is NEVD. As current density is represented as a vector quantity, I can write J vector is equal to NEVD vector. NEVD vector. So current density is a vector quantity. This is given by the expression J vector equals NE into VD vector. NE into VD vector. And in the previous section, we have discussed about the expression for drift velocity as Vd equals minus of E, capital E, divided by M into tau. This is the relaxation time. Tau is the average relaxation time. E is the electric field applied. Small e is the charge of the electron. M is the mass of the electron. Vd is the drift velocity. As Vd is the vector quantity, Vd vector is equal to minus of E into E vector divided by M into tau. So we already had the expression for drift velocity as Vd equals E by M into tau. Now you substitute this drift velocity in this expression. Let me say this is equation number 5 and this is the equation number 6. Substitute 6 in 5. Substitute 6 in 5. What will we have? We can write J vector is equal to N E minus E vector divided by M into tau. So I can write this as minus of N E square E vector divided by M into tau. Actually, N is a constant for a given metallic conductor. E, M, tau are all constants for a given metallic conductor. So I can write this is equal to minus of N E square tau divided by M into E vector. So J vector is equal to minus of N E square tau divided by M into E vector. I can replace this constants N E square tau divided by M as a single quantity, single constant, which is sigma into E vector. Sigma into E vector. So J vector is equal to sigma into E vector. And what is this sigma? What is this sigma? Sigma is called current. So sigma is conductivity. Sigma equals N E square tau divided by M. This is called the conductivity of the conductor. Conductivity of the metallic conductor. Conductivity of the conductor. What is the unit of sigma? This is said to be mho. For resistivity or resistance, it is ohm. Resistivity ohm meter. Conductivity, this is mho meter inverse. Mho meter inverse. Sigma equals n square tau divided by m. N is the constant, E is the constant, tau is the constant, m is the constant. All these constants are replaced by a single constant, sigma. We call this as the conductivity of a given metallic conductor. So it depends upon the material wire. It does not depend upon other factors. It does not depend upon the size and shape of the conductor. It depends upon the material wire. Sigma has the unit mho meter inverse. But conventionally, from this expression, J vector equals minus of sigma into E vector, we have a negative sign. We have a negative sign. And this has been obtained from a drift velocity expression. But what we know actually is that conventional idea speaks like this. The current always flows from positive potential to negative potential. In the sense, the electric field whose direction is always from positive to negative. Current flow will also take place from positive to negative. If it is the case, then the current density should also act along the direction of the electric field. But this expression says that there is a negative sign, which indicates that the current density and the electric field are acting in the opposite directions. No. By convention, or if you are applying the conventional idea, we can write this expression without the negative sign, like J vector equals sigma into E vector. Why? Conventionally, we used to say the charges tend to move in a direction opposite to the electric field. In a direction opposite to the electric field. Current flow always takes place in a direction opposite to the direction of flow of electrons. Why this idea has been taken? Before the discovery of electrons, current was discussed. So people were not aware of the flow of electric current. What makes the current to flow? Initially, people thought that there is something which is flowing from higher potential point to lower potential point. They do not know, they are not aware of the existence of electrons. After they found the existence of electrons, and also they came to know that the electrons possess negative charges, they explained that the current flow is due to the flow of electrons. But thing is that initially they had a discussion by considering that the current flow takes place from high potential to low potential. But the electrons tend to flow from low potential to high potential, which is in a direction opposite to the direction of flow of electric current. So electron flow direction is opposite to the direction of conventional current. So people do not want to change this idea. So they are following the conventional idea that the current always flows from high potential point to low potential point, which in turn explains that the electrons move opposite to the direction of conventional current always. By considering that idea in mind, we are bringing out this relation that J vector is equal to sigma into E vector. This negative sign has been omitted. Why? We are applying the conventional idea that the current density must act in the direction of the electric field vector. So J vector is equal to sigma into E vector. Also, we can write E vector is equal to rho into J vector. E vector is equal to rho into J vector. I will explain you why I am writing E vector equals rho into J vector. See the notations. This is sigma. This one is rho. Sigma is conductivity. Rho is resistivity. Because the idea is very simple. Sigma and rho are inversely proportional. Sigma and rho are inversely proportional. So if I keep the E on the right hand side itself and sigma is taken to the denominator of the left hand side, then 1 by sigma will be rho. So E vector is equal to rho into J vector. So J vector and E vector can be related like this. J vector equals sigma into E vector. Here in this particular case, this J vector is the current density which acts along the direction of area vector. Which acts along the direction of area vector. As I told you, current density is a vector quantity. J vector is equal to I divided by A. If you look at this expression, you may wonder there are two quantities, current and area, which brings out this current density. Current is scalar, already noted, because it does not obey the law of vector addition. If any quantity must be considered as a vector quantity, then the quantity should obey all the vector laws, but the current does not obey the vector law of addition. So current is taken to the scalar category, but area is a vector quantity. The normal drawn to the area denotes the direction of the area vector. If I am drawing this as the normal or A vector, then this gives you the direction of area vector. A is the area, A vector denotes the direction of area vector. So J vector is equal to I divided by A vector. J vector equals I divided by A vector. And here this J vector acts along the direction of area vector. This is how we have considered. But thing is that if the area vector is not exactly acting along the direction of flow of current, let me say, if area vector is making some angle theta with the direction of flow of current, then the current density can be calculated as, current density can be written as J vector equals I divided by the component of area vector which acts along the direction of current. So if I resolve this into two components, this one can be taken as AY and the another component can be taken as AX. So I can write the component which acts along the direction of flow of current, from which we can calculate the current density. J vector equals I divided by AX. This is nothing but I divided by A cos theta. I divided by A cos theta. So J equals I divided by AX is J equals I divided by A cos theta. Actually, I can write this as J, simply J. I can write this as simply J. J equals I divided by AX, which is equal to I divided by A cos theta. And I can be taken as J A cos theta. A vector, modulus of A vector, modulus of B vector cos theta is nothing but J vector dot A vector. So current is taken as the dot product of J vector and A vector. I equals J vector dot A vector. Once again, this expression reveals that the current is a scalar quantity. Current is a scalar quantity. If product of two vectors results you in a scalar, then, or if the two vectors are taken a dot product, then the resultant quantity must be a scalar. So J vector, current density, is a vector quantity. A vector, area vector is a vector quantity. If they are to taken a dot product, the dot product of these two vectors will result you a quantity which is nothing but a scalar. So once again, this reveals that, this expression reveals that current is a scalar quantity. So we already got the expression current density J vector equals sigma into E vector. Also, we can write E vector is equal to rho into J vector. As I told you, the value sigma, which we discussed, is nothing but conductivity. Conductivity sigma can be related with resistivity like this. Conductivity and resistivity are inversely proportional. Sigma is inversely proportional to rho. Sigma is inversely proportional to rho. If sigma equals n e square tau divided by m, then rho will be m divided by n e square tau. M divided by n e square tau. This rho is called resistivity. Rho is called resistivity. Its unit is ohm meter. Resistivity, its unit is ohm meter. It's a constant, and it is a constant for a given material. And this resistivity varies from material to material. For a given material, resistivity is a constant. So rho depends only on material. Also, it depends upon the temperature and pressure. So this has a dependence. So rho depends upon material, temperature, and pressure, and it is independent of size and shape. Independent of size and shape. So resistivity, or in other words, resistivity can be represented as specific resistance. Any physical quantity which is given a prefix specific, then that quantity must be a constant. If I say specific resistance or specific rotation or specific gravity, all these quantities are constant because it is specified. So it is applicable only for a specific data given. So specific resistance or resistivity, electrical resistivity, has got the unit ohm meter and its expression is m by n square tau. It depends upon the material wire. Also, it depends upon the temperature and the pressure conditions, but it is independent of the size and shape of the conductor. It is independent of the size and shape of the conductor. So what all we discussed so far in the microscopic model of current is that when you are applying electric field across the metallic conductor, how the flow of current takes place inside the conductor. This is what is discussed in the microscopic model of electric current, where we calculated the total number of free electrons in a given volume of the conductor, and they have already given small n be the number of free electrons per unit volume. So we have calculated the total number of free electrons. If E is the charge of the electron, then we can calculate the total charge of the electron as dq. From dq, we have calculated the current as I equals dq divided by dt. And by calculating current, we started calculating the current density. Current density is nothing but the flow of current through a given cross-sectional area of a conductor, J equals I divided by A. And from that, we have derived an expression, a relation between current density and the drift velocity, which is J vector is equal to J vector equals the NEVD vector. J vector is equal to, you can just look at the expression here. You can look at the expression. Current density and the drift velocity can be related as J vector equals NEVD vector. And drift velocity VD vector is nothing but minus of E by M into tau. On substituting drift velocity and simplifying, you are getting the expression J vector equals minus of NE square tau by M into E vector. This NE square tau by M is nothing but a constant for a given metallic conductor. We call it conductivity. So J vector equals minus of sigma into E vector. And the unit of conductivity is mho meter inverse. And if you look at this expression, there is a negative sign, which is there in J vector equals minus of sigma into E vector. But conventionally, we always used to say the current flow takes place in the direction of the current flow takes place in the direction opposite to the drift of electrons. In other words, I can say current flow takes place in the direction of the applied electric field. So current density should also act or flow in the same direction as that of the applied electric field. So J vector must be represented as plus of sigma into E vector because I am applying convention here, and E vector is equal to rho into J vector. And what is this rho? It's nothing but the reciprocal of conductivity. Sigma and rho conductivity are sigma and rho are inversely proportional. Sigma and rho are inversely proportional. So sigma is inversely proportional to rho. So I am replacing sigma in terms of rho as E vector equals rho into J vector. What is sigma? Ne square tau by M. What is rho? M by Ne square tau. Reciprocate. M by Ne square tau. A rho is called resistivity or specific resistance. Its unit is ohm meter. It depends upon the material and temperature and pressure, but it is independent of the size and shape of the conductor. And moreover, when you speak about current density, J equals I divided by AX, which is I divided by A cos theta. I equals J A cos theta. I equals J vector dot A vector. This indicates that the current is once again a scalar quantity because When current flow takes place along the direction of area vector, we can simply write J vector equals I by A vector, or I equals J into A. But when the area vector makes some angle theta with respect to current, then we have to take the component of A vector. The component of A vector which is acting along the direction of current. Here AX is the component. AX is A cos theta, AY is A sin theta. So instead of AX, I am substituting A cos theta. So I am getting I equals JA cos theta. A B cos theta is nothing but A vector dot B vector. So I equals J vector dot A vector, which gives you the dot product of our current is the dot product of two vectors, J vector and A vector. Once again, it reveals that the current is a scalar quantity. Right. Next thing, we shall go on with the calculation of macroscopic model of electric current, which is nothing but Ohm's law. As a continuity, we are going to speak about the macroscopic model of electric current, which is nothing but Ohm's law. So I can continue here. Macroscopic model of electric current, which is nothing but Ohm's law. We shall now speak about Ohm's law. George Simon Ohm, a German scientist who brought out a relationship between the applied voltage, the current flowing through the conductor, and the resistance of the material wire. So he brought out the relationship between these three physical quantities based on the relation what we have obtained in microscopic model of electric current. J vector equals sigma into E vector. J vector equals sigma into E vector. So from this expression, we are going to calculate the Ohm's law. So idea is very simple. Idea is very simple. Let us consider the same thing. Same diagram is considered. Conductor of length L is taken. Its area of cross section is A. Area of cross section is A. The ends of the conductor are applied with a source of potential difference, let us say V, so that the electric field acts along this direction. J vector acts along this direction. J vector acts along this direction. J vector acts along this direction. And then current flow also takes place along this direction. But electron drift takes place in the opposite direction. Drift velocity of electrons takes place in the opposite direction. We have seen the diagram here. So we are applying a potential difference V across the ends of the conductor, which makes the charge carriers to move in a definite direction to given cross-sectional area of a conductor, which results in a flow of current. As the current flows, they are opposed by the movement of electrons as well as the positively charged vibrating ions, so that there is certain amount of resistance offered to the flow of current by the metallic conductor. And George Simon Ohm brought out the relationship between all these three physical quantities. They applied potential difference, then the current flowing through the conductor, and the resistance of the metallic conductor. Resistance of the metallic conductor. And he obtained this expression from the magnitude of current density. J equals sigma into E. J is current density, sigma is conductivity, and E is the electric field. E is the electric field. In electrostatics, we have seen electric field is the ratio of potential difference divided by distance. E equals V divided by D. E equals V divided by D. E equals V by L, from which I can write V equals E into L. V equals E into L. If I substitute for this V in this particular expression, I can write J equals sigma into V divided by L. J equals sigma into V divided by L. So what are we doing here is that we obtained a relationship for current density and electric field. J equals sigma into E, where E is the potential difference divided by distance, So if you substitute for E, electric field, we will be getting J equals sigma into V divided by L. Also, we already saw current density is the ratio of our current density is given as defined as the current flowing through the given area of cross section of a conductor. J equals I divided by A. We already have one expression here. Current density can also be expressed as I divided by A. Relate this to what will you have? I divided by A is equal to sigma into V divided by L. Sigma into V divided by L. We are going to bring out the relationship between V, I and R. So I can write V equals I into L divided by sigma into A. So I can write I into L divided by sigma A. This L divided by sigma A is replaced as R, a quantity called resistance. R is the resistance of the material wire, or R is the resistance offered to the flow of current by a conductor when it is applied by a potential difference of V. So this is called Ohm's law. In other words, I can call this as the macroscopic model of current. Macroscopic model of current, which relates the three important physical quantities: voltage, current, and resistance. V equals IR. Here, R is the resistance of the metallic conductor, which is L divided by sigma into A. L divided by sigma into A. R equals L divided by sigma A. This is called resistance of the conductor. This is called the resistance of the conductor. R is the resistance of the conductor. What is its unit? Ohm. Its unit is ohm. This expression can also be represented as R equals rho L divided by A. R equals rho L divided by A. Already we saw the relation between conductivity and resistivity. I already told you rho and sigma are inversely proportional. Rho and sigma are inversely proportional. So I can write R equals rho L divided by A. In terms of resistivity, resistance can be expressed as R equals rho L by A. In terms of conductivity, we can represent resistance as R equals L divided by sigma into A. Both these relations are the same name, resistance of the conductor. Its unit is ohm. Its unit is ohm. So from this expression, V equals IR, we can write R equals V divided by I. R equals V divided by I. We can define resistance here. Resistance of a metallic conductor is defined as the ratio of voltage applied across the metallic conductor to the current flowing through the conductor. To the current flowing through the conductor. So resistance of a metallic conductor is defined as the ratio of voltage applied across the ends of the conductor to the current flowing through the conductor. R equals V divided by I. So I am defining resistance here, where R equals V divided by I. It defines that resistance of a conductor is defined as the ratio of voltage applied across the conductor to the current flowing through the conductor. To the current flowing through the conductor. So V equals IR. This expression can be taken in a triangle like this. Can be taken like this. If we want to calculate any problem, we can do it with this expression: V equals IR, I equals V divided by R. See this one? I is V by R equals V by I. So if you want to find out any particular physical quantity, then look at this triangle. We can easily identify it. V equals IR, I equals V by R equals V divided by I. Any physical quantity can be found by knowing the other two physical quantities. So idea is very simple. V equals IR. This is Ohm's law. In other words, I can call it as macroscopic model of current. This is a scalar form of Ohm's law. In other words, I can say V equals IR is the scalar form of Ohm's law. If V equals IR is the scalar form of Ohm's law, what is the vector form of Ohm's law? J vector equals sigma into E vector. J vector equals sigma into E vector. So vector form of Ohm's law is J vector equals sigma into E vector. Scalar form of Ohm's law is V equals IR. From this expression, we are defining resistance of a conductor R equals V divided by I. Also, we have to define what is this rho, what is this electrical resistivity. We shall speak about the electrical resistivity after this one. Before speaking about electrical resistivity, we have to speak about two important factors here, or two important ideas here, that when you look at the expression V equals IR, when you look at the expression V equals IR, resistance of a material wire for a given length, for a given area of cross section is a constant. So for a given metallic wire, resistance is a constant. If the length changes, resistance changes. If area of cross section changes, then also the resistance changes. We are going to draw a graph by taking voltage along x-axis and the current along y-axis. Voltage is a independent variable, so it is taken along x-axis. Current is a dependent variable, so it is taken along y-axis. And the graph obtained is a straight line. Graph obtained is a straight line. As voltage increases, the current also increases correspondingly. When you take a slope for this graph, we can have, this is delta I, this is delta V. When you calculate the slope, this is delta I divided by delta V. This will give you conductivity. Direct slope gives you conductivity. The reciprocal of slope, I'm sorry, this will give you conductance, not conductivity. Sorry, have to use this one, conductance. G, conductance. Conductance. The reciprocal of slope gives you resistance. Delta V divided by delta I. This will give you the resistance. This is an important one more question which you should know. The slope of a VI curve in Ohm's law gives you conductance, not resistance directly. When you take the slope, reciprocal of slope, you will get the value of resistance. So the reciprocal of slope gives you the value of resistance. And we can say here, current varies linearly with I. In this graph, we can infer that the current varies linearly with V. In the sense, as V increases, correspondingly the current also increases. So this is a linear plot. This is a linear plot. Thus, we can say here, the material or conductors which obeys this Ohm's law are said to be the linear conductors of electricity. Those material or those conductors which obeys Ohm's law are said to be linear conductors of electricity. Which obey Ohm's law are said to be linear conductors of electricity. There are some other conductors or some other conducting material like diodes. We can say the variation of current with respect to potential difference is not linear. See, if you look at the graph, you can see the curve is not linear. In the sense, current is not varying directly with the applied potential difference. So this is said to be a non-linear conductor of electricity. Non-linear conductor of electricity. Non-linear conductor of electricity. So it does not obey Ohm's law. Does not obey Ohm's law. So those conductors which obey Ohm's law are ohmic conductors. Those conductors which obey Ohm's law are termed ohmic conductors. Which does not obey Ohm's law are termed non-ohmic conductors. See, this is a non-linear conductor of electricity. Actually, a diode does not obey Ohm's law. The behavior of a diode, which is a conducting medium, which shows a non-linear plot. So this is a non-linear conductor of electricity, it does not obey Ohm's law. So it's a non-ohmic conductor. It's a non-ohmic conductor. So we could able to distinguish the nature of the conductor on the basis of this Ohm's law. If the conductors obey Ohm's law, then they are called ohmic conductors. If they do not obey Ohm's law, they are said to be nonlinear conductors of electricity. So they are non-ohmic devices. They are non-ohmic devices. These materials have more complex relationship between voltage and the current. And the plot of I versus V for a non-ohmic material is non-linear, and they do not have a constant resistance. So if you calculate the value of resistance, if you in this curve, if you calculate the value of resistance will not be a constant. R is not a constant in this case. Whereas in this graph, those conductors which obey Ohm's law, R is a constant. R is a constant. So in nonlinear conductors, R is not a constant. R is not a constant. Now we shall speak about the electrical resistivity here. Electrical resistivity. What is electrical resistivity? We already saw. R equals rho L divided by A, and this rho is called electrical resistivity. I told you rho is called electrical resistivity. So we can write rho equals R A divided by L. Rho equals R A divided by L. If I consider the length of the conductor as 1 meter and the area of cross section of the conductor as 1 meter square, then rho will be simply equal to R. Then I can define electrical resistivity here. Electrical resistivity of a metallic conductor is the resistance offered to the flow of current. Resistance offered to the flow of current by the conductor of unit length having unit area of cross section. So electrical resistivity of a metallic conductor is defined as the resistance offered to the flow of electric current by a conductor of unit length having unit area of cross section. If you look at this data, you can be very clear that the dimension of the conductor is taken as 1 meter. The length of the conductor is taken 1 meter. Area of cross section is taken 1 meter square. And this won't change while calculating the electrical resistivity. So electrical resistivity always remains a constant, where electrical resistance changes. Electrical resistance for a given metallic wire changes with size and shape, but not electrical resistivity. Electrical resistivity depends upon the nature of the material. Also, it depends upon the temperature as well as the pressure. Temperature and pressure. Rho equals R. So from this idea, or from the Ohm's law, we obtained V equals IR, where R equals rho L divided by A, and rho is electrical resistivity. And this electrical resistivity idea will be discussed in the next session. Right? Electrical resistivity idea will be discussed in the next session. We shall now calculate some of the problems related to this Ohm's law. First, you should remember or recall that what is vector form of Ohm's law? It is J vector is equal to sigma into E vector. What is scalar form of Ohm's law? V equals IR. Why do we call it as microscopic model of current or microscopic model of Ohm's law? Because it's going to explain the behavior of charge carriers when the conductor is applied with external potential difference. So it establishes an electric field E inside the metallic conductor, which makes the charge carriers to move in a definite direction, resulting in a flow of current. So it simply explains about the flow of electric current with the application of external electric field. Ohm's law in the macroscopic model relates the external potential difference applied, current flowing through the conductor, and resistance R of the conductor. We can simply say here the current flow through the conductor I equals V by R can be expressed like this. Ohm's law can be expressed like this. The current flowing through the metallic conductor is directly proportional to the potential difference applied between the two ends of the conductor and is inversely proportional to the resistance offered by the conductor. Greater the amount of potential difference, greater is the flow of electric current. Lesser the amount of potential difference, lesser is the flow of electric current. Greater the value of resistance, lesser is the current. Lesser the value of resistance, greater is the flow of electric current. This is all about Ohm's law. We shall now solve some of the problems related to this. A copper wire of cross-sectional area of 0.5 millimeter square. Example problem is given. Example 2.3. A copper wire of cross-sectional area of 0.5 millimeter square. Area is given 0.5 millimeter square. And carries a current of 0.2 ampere. If the free electron density of copper, number density of electrons, is 8.4 into 10 power 28 meter power minus 3, then compute the drift velocity of free electrons. So you are asked to calculate the drift velocity of the free electrons. So given data is this one. We know the relation connecting current and the drift velocity is I equals NA E VD. Drift velocity is asked. VD equals I divided by NAE. I divided by NAE. Substitute the value of current here, 0.2. Number of free electrons per unit volume is 8.4 into 10 power 28. Area of cross-section of the conductor is 0.5. It is given in terms of millimeter square. Milli is 10 power minus 3. So milli square is 10 power minus 6 into E charge of the electron, 1.6 into 10 power minus 19. So I can cancel out the powers here. 19, 25. This goes off. 1 plus 3 is left. Plus 3 is left. If you look at this, we can write 2 into 10 power minus 1 divided by 8.4 into 0.5 is taken 1 by 2 for simplicity. And this is 1.6. I'm taking this 2 to numerator. And there is 10 power plus 3 left. 10 power 3 is taken to the numerator. This 2 is also taken to the numerator. So I can write 4 into 10 power minus 4 divided by 8.4 into 1.6. 8.4 into 1.6. Simplify this further. This is equal to, if 4 is cancelled, this is 0.4. So 1 into 10 power minus 4 divided by 8.4 into 0.4. 1 divided by 8.4 into 0.4 will be hardly 3.37 into 10 power this minus 4. 1 divided by 3.37 is 0.297. When you divide this value, 1 divided by 3.37, it is 0. 1 divided by 3.37 is 0.297. 10 power minus 4. I can make it 0.0297 into 10 power minus 3. Simply 0.03 into 10 power minus 3 meter per second. So drift velocity VD is 0.03 in 10 power minus 3 meter per second. This is one problem. Idea is quite simple. Simplification is also simple. You have to apply some idea to simplify it. Then we shall go on to the next problem. Determine the number of electrons flowing per second through a conductor when a current of 32 ampere flows through it. See, this is 2.4. If a current I of 32 ampere is flowing through a conductor, they are asking you to calculate the number of electrons flowing per second. Number of electrons flowing through the conductor per second. As you know, the expression for current is I equals Q divided by T. From electrostatics, Q equals NE. divided by T. So if you want to calculate the number of free electrons passing through the given conductor, then I can write N equals I into T divided by E, I into T divided by E. I is given 32 ampere, time is 1 second, E is the charge of the electron, which is 1.6 into 10 power minus 19. To cancel this, this is 20. So 20 into 10 power plus 19. And this is 2 into 10 power plus 20 electrons. So I can say 2 into 10 power plus 20 electrons will flow through the given conductor in 1 second when a current of 32 ampere is made to pass through the conductor. When a current of 32 ampere is made to pass through the conductor, 2 into 10 power 20 electrons will happen to flow through the conductor in 1 second. See, this is the expression. I equals Q divided by T. Q charge equals Ne. Number of N is the integer. E is the charge of the electron. So Q equals Ne. N equals I into T divided by E. This expression is quite simple, from which we are calculating the number of electrons passing through the conductor in 1 second, which is 2 into 10 power 20 electrons. Now, these are the problems which are related to drift velocity and electric current. We shall now solve another problem which is related to Ohm's law. Related to Ohm's law, I can say this is example 2.5. Example 2.5. A potential difference of 12 volt is applied across a resistance of 24 ohm. 24 ohm. What is the current through the resistor? What is the current through the resistor? By Ohm's law, we can write I equals V divided by R. I equals V divided by R. V is 12, R is 24. So when you cancel this out, you will have 1 by 2, which is 0.5 ampere. 0.5 ampere. So 0.5 ampere current will flow through the metallic conductor of resistance 24 ohm when it is applied with a potential difference of 12 volt. So these are the problems which are related to Ohm's law. Actually, there are so many number of problems involved in the idea of resistivity and conductivity, as we are bound to Ohm's law and this microscopic and macroscopic model of Ohm's law. We are simply solving very simple problems. We shall go on with more number of problems, more number of examples. We can wait for a while. I'll give you another problem. We shall go on with another problem here. Calculate the electrical conductivity of the material of a conductor of length 3 meter, area of cross section 0.2 millimeter square, and having a resistance of 2 ohm. You are asked to calculate electrical conductivity. Calculate electrical conductivity if the conductor of length 3 meter, area of cross section is 0.2 millimeter square, 0.02 millimeter square, having a resistance R of 2 ohm. So how can you calculate electrical resistivity here? Calculate electrical resistivity, idea is simple. You know the formula connecting resistance and resistivity. R equals rho L divided by A. We are asked to calculate rho. Rho equals RA divided by L. Resistance is 2 ohm. Area of cross section is 0.02. It's millimeter square, so 10 power minus 6 divided by length of the conductor is 3 millimeter. So I can make it 2 into 2 into 10 power minus 8 divided by 3. So 4 by 3 into 10 power minus 8. 4 by 3 into 10 power minus 8. So we will have 1.33 into 10 power minus 8 ohm meter. This gives you electrical resistivity. Also, we can calculate electrical conductivity in this expression. Conductivity can be calculated as sigma equals 1 by rho. Conductivity value can be obtained by taking 1 divided by, actually I got resistivity as 4 by 3. I got 4 by 3 into 10 power plus 8. If this plus 8 minus 8. So if it goes up, it will become 10 power plus 8. 10 power plus 8. 4 by 3 will become 3 divided by 4. So 3 by 4 is 0.75 into 10 power plus 8. So it is 75, sorry, this is 75. This is 75 into 10 power plus 6. Actually, this is ohm meter. This one is mho meter inverse. This is conductor. 75 into 10 power plus 6 mho meter inverse. Or otherwise, I can write it as ohm inverse meter inverse. This is ohm inverse meter inverse. You are reciprocating it. Actually, this is the Greek alphabet. Omega is the Greek alphabet. Omega, capital letter omega. Greek alphabet, capital letter omega. So omega inverse, meter inverse. So this is another problem related to resistivity and conductivity. So we will be discussing with electrical resistivity, then resistances in series parallel in the next session. This is all about the microscopic model of electric current and macroscopic model of electric current, Ohm's law. Ohm's law idea has been discussed so far. We shall discuss about the other ideas later. Thank you.